Oh, hell yeah. All right, another infinite amount of time on the clock. And we're just learning about acceleration with polar coordinates. You have an origin, you have a radius, and you have either a velocity or an accelerator. Anyway, we get it. So this one's real simple. Hey, look at this. Our radius don't change. So a plane is flying. There's Earth way down there. I think we get it. And then a plane is doing a vertical loop. Now, it looks like the plane's upside down, but no. It's just right side up. And, there's a people person right there, doing the navigational flip. Anyway, so it's doing a vertical loop. And if that person is standing on a scale in the plane, how much are they going to weigh? And does this even say, look at this, what's the pilot's weight? Good, all right, that's weight, because kilogram, that's mass. The pilot's always 60 kilograms unless he's getting a haircut, and then he might be a little bit less. But I don't know if he's doing a haircut, while doing this fancy maneuver. But this loop is pretty huge. It's 400 meters. I don't know what that is. But I do know, like, hey, if you just multiply by 3, that's 1,200 meters. And I don't know, oh no, that's 1,200 feet. I don't know what that is either, but I do know that 5,000, something is a mile. Whoa. So this is like it's not a quarter mile, but it's quarter mile, Oh, yeah, that's a quarter mile. This is a quarter mile, and this is a quarter mile. This is a half mile loop, you know what I mean? So that's a half mile from there to there, just going in a half mile loop. That's pretty amazing. Now we know what 400 meters is. I don't even know if that's even right. But anyway, what we want to... Okay, so this is the equation for acceleration is r dot... No. Yeah, r dot er, and this is a vector, plus r dot omega e phi plus r dot omega e phi. Well, there's two of those. Friggin' A. And then plus r alpha e phi plus r omega squared er. Oh, and these are all vectors. Okay, so dumb, because but guess what? Our radius is staying the same, so all we have to use is these two, and really it's just acceleration is radius times the change in angular acceleration, anyway, plus radius times omega squared. Okay, so this is acceleration. Okay, but it's going at a constant speed. So the angular speed is constant. This is angular speed. So there is no change. This is change in angular speed, change in time. Just like acceleration is change in velocity, change in time. If we know the velocity is constant, hey, there is no acceleration. Okay, but whoa, you just said if you have constant velocity, there's going to be no acceleration. Well, that's if you're going in a straight line. But the second you go in a circle, well, guess what? You know what I mean? If you're a point right here, well, you're constantly changing directions back to this point, because if you're just going in a straight lines that way, buddy, and you're always turning back in. So you need a force to keep you that way, which is tension. Tension in the string. If you're getting whipped around by a little string on something, woo, little tether ball. But anyway, I think we get it. Maybe you don't. You're just running through this. But this speed doesn't slow down, so this component goes to 0. So our acceleration is just r omega squared. Now that's still too much. It's still too much. But holy Toledo, if I'm an alien, the only thing I'm interested in is acceleration. You know what I mean? Constant velocity, you throw a stone into deep space, it's just doing a straight line. You know what I mean? Not even the stars are grabbing it in. We're talking just like deepest concepts of space. If a stone is getting thrown, it's got constant velocity, and there's no acceleration. If you are that stone in that real depressive, and that's going to happen, the heat death of the universe, or if you're ever feeling like that stone, you're not looking for extraterrestrial life. You're just looking for an acceleration. The second you feel a change in velocity, you're like, hell yeah, there's something else out there. There's another stone, and maybe you can, like, you know, spin around that, because that's all the Earth and the Moon do. But, you know, to you, to that stone in deep space, that is like finding alien life. So, anyway, so yeah, velocity constant, that sucks. But if we can figure out that there's an acceleration, now we got something. We got a force. That's a force of love, baby. And so, and it is. It's amazing. F equals ma. The fact that if you have an acceleration, that just means you have a force, which is crazy. It'd be like, hey, if you can identify acceleration, that means you have, you know what I mean, your weight in dollar bills. I didn't do it right, but if you find some acceleration, we'll times it by your mass, and you got your weight in dollar bills. F equals ma. And it really is amazing. You know what I mean? If you weigh something, but then somebody has a force, you know what I mean, on you, well, it looks like you're going to weigh a little bit less or a little bit more. So now we got to throw another 10 minutes on the clock. Alright, so we're done with this book, but the next thing I'm going to say is just the part where I pretty much totally get it wrong. We got to figure out, like, even, is that pilot, you know what I mean? It's, and we'll do a sheet. Is she going to weigh more or less? You know what I mean? Shouldn't have done a sheet on this one, because we're talking about weight. It could be a little, you know, too much going on. Anyway, just a people person pilot. His name is People Person. Okay, so we got the pilot, Mr. People Person Pilot, PPP. Is that People Person Pilot going to weigh less or more after that People Person Pilot does a full loop? Now, okay, so I was just thinking about it. I have no idea. Let's say it's just a flip of a coin. I don't want to flip a coin. I want to say, hey, this plane's going up, and then all of a sudden, it's going up real fast right here, and guess what? It hits the top here and kind of stops because now it's going down real fast here. So I would say, hey, if it's going up, you're like, whoa, you know what I mean? If this is an elevator that's going up, dang it, I gotta take this phone call. Oh, hell no. That was literally just a spam. They're literally like, okay, we got you on the line, but can you wait for our coverage specialist about your car? You know, that's crazy. Okay. Oh, but if this is an elevator, and I guess if you're just going up with constant velocity, your weight ain't different. But let's say your acceleration here is huge. Does that even make sense? Well, no. Well, so you're going constant velocity in an elevator, but at the top you got to stop. Okay, perfect. So if you stop, you're going to keep on going up, and then the elevator stopped. So there's forces, there's friction in the cable of the elevator that's stopping it, but you don't got a seatbelt on in an elevator. So you're literally going to weigh less. If you're on a scale, you're going to weigh less at the top. Perfect. So I'm just going to final answer say that this airplane thing weighs less at the top. But now get this. Let's say this is a horizontal circle. You know what I mean? Or you're just in deep space, but the Earth is down there. It don't matter. You're in deep space, and you still weigh 60 kilograms, and you want to do this half-mile, quarter-mile circle, half-mile, you know, anyway, and you got a string, and you're going, you're just getting, the question is you're holding on, and for whatever, you're just going that fast, you know what I mean? You're just traveling 400 meters per second into deep, which is about 1,000 miles an hour. Oh, no, it's a 400 meter radius. You're traveling 50 meters per second. More on that later. But what's the tension in the string? Well, let's do that one. Let's do that one first. Well, let's just say you're going horizontal. And what's this tension on the string? Because that's interesting. You're like, because here's the one that really makes it. This really makes it. So let's say you're in deep space. You're that potato, that rock, or whatever we called it. You know what I mean? The existence is over. We're just heat deathing it out. You're just you're just light years away from anything. You can't even see light. You're just a floating potato out there. But let's say you had a reminiscent of what Earth was, and an Earth was a circle that was a 24-hour circle. You know what I mean? And it had a huge diameter. Okay, and 6,000 meters radius? I forget. But anyway, no, 600 mile radius, 6,000 miles. Okay, anyway. So let's say that there was a string. Now we really got a time zone is 1,000 miles. Okay, and there's 24,000 miles around the circumference. You should know that. 24,000 miles in a circumference. That's how you get there real fast. And then divide by 3. 24,000 divided by 3. Well, that's 8,000. But 24,000 divided by pi, well, that's 7,600. Oh, okay. We're just going to say 7,600. So you have a string attached to just some alien particle that don't have any mass, and it's 7,600 miles long, and you're that potato, and you actually get to grab the end of the string, and you're like, sweet, this feels like Earth because I'm going 1,000 miles per hour, and it's going to take me a whole 24 hours to get back to the same point. So there's going to be tension on this string. That was the whole setup. Hey, there's going to be tension. How much tension actually holds you to the center of the Earth when we rotate around it? That's the whole thing. That's the acceleration, well, is equal to that radius, omega squared. So what the hell is omega? Well, that's radians per second. So now, that's crazy. I don't like that. But what I've always said, hey, you have a circle. There's 6 radians in a circle. Just like, hey, there's 3, just like pi is 3.14. Pi is 3. That's all you got to know. A circle is 6. Actually, a circle is 6.28 because pi plus pi is 3.14 plus 3.14. Okay, I'm just on repeat here. Okay, but anyway, so how do we get radians? Again, well, there's 6 of them in a full circle. And you're saying that, so 1 radian is just a sixth of a circle? 1 radian is equal to a sixth of a circle? Sure. And we know the circumference is 24,000 miles. So 1 radian is just a sixth of that. So 24 divided by 6, well, that's 4,000. So 1 radian is equal to 4,000 miles. And it's not too accurate, but that's 1 radian, 4,000 miles. And 24, so radians, and what's our radians per second? We got it. Well, it's 6 radians to do the full 1 day, equals 1 day, which is, 1 day is 24 hours. Times, 1 hour is 3,600 seconds. You know, you can do it. 24. So you got 24 times 3,600 seconds. Well, that's a lot of seconds. That's 86,400 seconds. But sure, so 6 radians is 86,400 seconds. Well, we just want radians per second. Well, 6 divided by that. You know, 86,400. Okay, so we get a really tiny number, and we'll just store that as x, because it's a 0.1234 zeros, a 6, and a 9, and a 4. That's how many radians per second. So not many radians per second. It's going to take you 24 hours. Okay, so we got that real small number. We stored it in our calculator as x. Well, shoot, we got it. That's x, and we know the radius. I just guessed 7,600 miles, but we need that in meters. Okay, so so our circumference is 24,000 miles. Okay, 24,000 miles. Well, 1 mile is 5,280 feet. Whew. And then 1 foot is 12 inches, and then 1 inch. Well, that's 25.4 millimeters, and 1,000 millimeters is 1 meter. So we got to go 24,000 times 5,280 times 12 times 25.4 divided by 1,000, and we'll get meters. You know what I mean? That's crazy. But we're going to get our circumference in meters. So let's do it. 24,000, because we're pretty accurate on that, times 5,280 times 12 times 25.4 divided by 1,000. Hell yeah. So that's how many meters. We're just going to store that as the alpha C. That's circumference. And it's like 3 million. It's 38 million. 38 times 10 to the 6 meters. Oh, I don't even know if that's right. It don't feel right, but that's all right. Yeah. If one time zone's 1,000 miles, and you got 24,000 miles. 24,000 miles is the circumference. Final answer, miles to feet. 1 mile is that many feet. 1 foot is that many inches. So you got more inches. We got more millimeters. 1 inch is 25.4 millimeters. Yes, it's 2.54 centimeters. Okay, and 1,000 millimeters, well, that's a meter. Okay, and we're just going to divide by pi, because that's the, and then you get the diameter, stored as diameter. That's diameter in meters. Oh, and then divide by 2, and then you got the radius. Man, I hope I did this right. But okay, so we get the radius. Yeah, the radius is 6 million. I remember that. The radius is 6 times 10 to the 6 meters. Perfect. Okay, now we're back in business. Okay, because I remember that. Radius in meters of the Earth, 6 times 10, 6 million. 6 million. Good enough. But we got it stored in our calculator to get real accurate. And then we just do radius, 6 million. Radians per second, hella tiny. You know what I mean? Very small degree change. 15 degrees every hour. You know what I mean? For the flat earthers. Okay, and we got to square that small number. That's crazy. So x is that small number. We're going to square it, and then we're going to multiply by, well, 6 times 10 to the 6. That's a big number. And then so alpha r, get that in there. Okay, so now we get acceleration. Acceleration is 0.0296 meters per second squared. Change in velocity and now what the hell is the change in velocity? We said we were going 1,000 meters per second this way. Well, yeah, you need to change your velocity just a little bit back towards that radius. You know what I mean? Just to keep this, else you're just going to go in a straight line. But you got to change your change your velocity. Your velocity towards the radius has to be a little bit. So your change in velocity is the acceleration back towards the radius. If you don't have a change in velocity, because right here, your velocity this way towards the radius, velocity towards the radius is 0. You got no velocity going towards the radius. But the second you hold on to that string, well, hey, now you're actually going to be moving towards that radius. If you didn't hold on to the string, you're just going to continue in a straight line, like normal. No acceleration, constant speed. But since you decided to hold on to this string, there's going to be tension in the string. And your change in velocity, well, is 0.02 meters every second. Or 0.2 meters per second every second. So it's a real small change, but it's there. And F equals ma. So if we weigh 60 kilograms, like this pilot, hey, we're going to have an acceleration of 0.03 meters per second squared. Okay, and kilograms times meters per second squared, that's equals to newtons. So 0.03 times 60, well, you got 1.8 newtons. Okay, so you're going to feel a tension in this rope of 1.8 newtons. All right, get some more time on the clock. All right, and what the hell's a newton? Well, a newton ain't much. 1 newton is a McDonald's hamburger. It's a quarter pounder. 1 newton is a quarter pounder. Okay, we got 1.8 of those. Well, looks like you got 2 quarter pounders. So not even a half a pound. So basically, you're going to have to hold a 16-ounce beer. So that's why I like this problem. Because, you know what I mean? If you're that potato floating in deep space and still alive just by some spiritual, you know what I mean, witchcraft, anyway, and then someone gives you an imaginary pint glass to hold on to that's connected to a string that's 7,600 miles long. reminiscent of the Earth, well, hang on to that pint glass for 24 hours and you'll be back in the same place that you were, and the pint glass will feel as heavy as a pint glass did when you were reminiscent on Earth. Okay, so that's amazing. So the gravity, all the molecules of Earth, where you're just like, hell yeah, that's a lot of that's more than two. I weigh more than 2 McDonald's hamburgers. Hell yeah, gravity of Earth, that's crazy. But the extra little acceleration because you're spinning, well, that's kind of small. Okay, but let's say you spin faster. You know what I mean? Well, isn't that acceleration going to be faster? Yes, and isn't the tension going to be more in this string? Yes. So if you're trying to hold on, so let's go right here. Let's say I'm trying to hold on to this plane, you know what I mean, with my hand. I'm gripping with my hand, and but we're still doing this way. So not vertical, so we're taking this and going horizontal. But if you have a horizontal circle and a plane going, and I'm just trying to hang on for gosh darn dear life, the tension in my arm, well, let's do that right now, because that might help us with this problem. Whoa, I don't even know if you can see anything. Okay, I was just off the screen. But anyway, so if I'm horizontally hanging on, well, so now we can plug it in. So yeah, acceleration is that radius omega squared, and all we know is the velocity though. So our velocity is 50 meters per second, but omega is equal radians per second. What the hell's a radian? That's what I always say. What the hell's a radian? Well, if I have a circle, well, that's 6 radians. Okay, and it's actually 6.28 radians, but let's just go with it. So we need radians per second. So we need, I think we need the circumference of the circle. Circumference of the circle is 2 pi r, which is 2 pi times 400 meters. Okay, got it. Once we get the circumference, well, let's just do it. 400 times 2 pi. Well, that's a 2,513 final answer, and that's in meters, and we're going 50 meters per second. So let's just divide by 50 meters per second. Seconds go upstairs, meters cancel, so divide by 50. Well, hell, it's going to take you 50 seconds to do this loop, whether you're horizontal or vertical. Okay, so we got 50 seconds of rotational time, and we need to figure out radians per second. Well, we're going to go 6.28 radians in a circle. So we do one full circle in 50 seconds. You divide these, then we'll get radians per second, which is 6.28, or just, if you want really accurate, 2 pi divided by 50. And, well, you would do 2 pi divided by, oh, weird. Yeah, you would do, oh, interesting, because we got 50 right here, and how did we get this 50 seconds? Oh, well, we did this divided by 50. So you go 2 pi 400 meters divided by 50. Then you get this number, which is 50, and then you do this, and then you go 2 pi divided by that. Well, I think the pi's just cancel right out, and I think you get 50 divided by 400. That was kind of a fun way to do it, but 6.28 divided by 50. Yeah. So, yeah, the pi's just cancel out. But anyway, the radians, you get 0.125 radians per second. And let's figure out what the velocity is. Because if you have radians per second, velocity, and radians is like, well, what the hell is a radian? Well, radians times radius is something useful. So radians per second times radius, well, that's going to be velocity. So 0.125 radians per second times your radius of 400 meters, 0.125 125 times 400. Whoops. 0.125 times 400. All right, it is 50 meters per second. All right, more time on the clock. All right, so that I love doing this because the second I get radians, like, it's just not intuitive for me, so I just have to go through that whole rigmarole of you know what I mean, figuring that out. But anyway, so now we got radians per second, which was 0.125 radians per second. Okay, so we got radians and we got radius. Our acceleration is 400 meters. That's the radius of the circle, times 0.125 radians per second. Okay, 0.125 times 400. Oh, no, 0.125 squared. I apologize. You got to square that stuff. So 0.125 squared times 400. Hey, we get an acceleration of 6.25. Well, that's a decent acceleration. Meters per second squared. And F equals ma. The mass is again was 60 kilograms, and we got acceleration of 6.25 meters per second squared. Now I guess you're just gonna have to remember, but F equals ma. F is in newtons, mass is in kilograms, acceleration meter per second squared. So kilograms meters per second squared, that gives you newtons. So times 60, hey, we get 375 newtons. Okay, I can dig. And divide by 4, basically, you know what I mean? You know, because it's 4 McDonald's hamburgers, 4 quarter pounders. No, 1 Newton is a quarter pound. So divide by 4, you get 93.75 pounds. Okay. And if this person was on Earth, you'd get 60 kilograms times 9.8 meters per second squared, and you get 60 times 9.8, and you would get 588 newtons. Divided by 4, hey, that's 150 pounds. Okay, so, we almost lost half of our weight. We either lost half of our weight or we gained it, but I swear, because this is vertical, it's like you're in an elevator and you're still going up. You're still going up, but the plane wants to go down, so you're going to weigh less. Can we prove that, though? Yes, because if you're going towards the ground real fast, well, like right here, like you're probably weightless. You know what I mean? Constant velocity down, it don't mean anything. It's the same thing as the elevator. Constant velocity up, it don't mean, if your constant velocity is straight up, you're going to weigh the same amount. You know what I mean? It don't matter. If your constant velocity is straight down, well, you're going to weigh the same amount. You can't tell if you're even moving. Constant velocity means you can't even tell if you're friggin' moving until you hit the ocean, and you're like, whoa, we were definitely moving. You know what I mean? So even that plane just stalled and fallen out of the sky, yeah, you'll still weigh the same. You know what I mean? No freebies there. But once you hit the ocean, yeah, you're going to weigh a hell of a lot. Your acceleration is almost infinite, and for a split second, you're gonna feel like the inside of a star. Okay, so yeah, final answer on the ground is going to be hella, because you hit the ground or you just hit the bottom of the circle. But on the top, it's going to be a hell of a lot. But does that make sense? Because there's tension in this string. Well, we just did it. We did it horizontally. We even did it horizontally. We did it this way and figured the tension in the string horizontally, and that's the same. You know what I mean? Hey, yeah, if you're not going in a circle and you just for whatever reason on a huge platform attached to the earth, yeah, the same thing. Or if you're just in an airplane falling out of the sky because somebody decided to stall the aircraft, sure, you're still going to weigh the same. If your velocity is terminal velocity, yeah, that scale is going to read what you have always weighed on Earth until you explode into the ocean. And then it's just going to be astronomically heavy. You're going to break that scale. Yeah, just to let you know. Anyway, So you have to use the extremes, even in language, to make math exciting at all. But if you use the extremes, you can kind of figure out what's going on. But the tension in that string, that's wild. Yeah, there's 93 pounds of tension. So when an airplane, so this is probably a real maneuver. That's why I like this problem. Get some more time on the clock. That's why I like this problem, because it's an actual real problem. A plane, so 50 meters per second, how do you get to miles per hour? Well, times 2, so 100 miles per hour. Is that right? Well, you can add 25% tip. So plus 25% tip. Well, what's 25% of 550? Have no idea. But what's 10% of 50? Well, that's 5. What's another 10%? 5. And what's another 5%? Well, that's 2.25. So you got 100 plus 12.5. So you 112.5 miles per hour. So this is a real slow moving aircraft. So very slow moving aircraft doing a very like large half-mile loop. Now, if you didn't get that from the problem, like literally just live in Canada for 4 years because American engineers are, the second you give them meters, I don't know, they're just going to think this is like the size of an apple. I have no idea. They don't know what so anyway, so for me, I have to do those, like 400 meters, well, times 3, get halfway there, and we did it. That was 1,200 meters. That was 1,200 feet. Still means nothing to me. You know what I mean? Well, what is that? What is that, 12 football fields? I have still no idea. So 5,000 is a mile. Okay, now we're talking. That's quarter mile. Okay, so anyway, it's really good to do that because everything is going to be in meters per second. All your F equals MA. You can't do F equals MA in normal units because else you got to break out that little critter called the slug. And if you're like, what the hell is a slug? Exactly. Europe 1, F equals MA, meters per second, kilograms, meters per second squared. Alright, so I think we did it, except the fact that there's tension in this rope. Yeah, you're going to have to hold on to 93 pounds. So could you even hold on? Yeah, so, we can hold ourselves. So yes, if you're on the pull-up bar, hell yeah, you can hold yourself up. Most people weigh 150, 200 pounds. And they can hold themselves up. So all you do have to do is hold on to 90 pounds for about 50 seconds, and you can hang on to that plane. You can literally hang on to that plane. Hopefully you're just strapped into the plane, but that's interesting. If you're hanging on to the outside, if you're doing, the new movie with Tom Cruise, you're hanging on to the outside of this plane for 50 seconds, well, yeah, you're going to experience 100 pounds of force on that bar, and your feet are just going to be flying through the air. So I'm not going into that, but that's literally what's happening if you're doing a horizontal loop. If you're doing a vertical loop, well, I would imagine it's still the same. Is that you're going to feel heavy. You're going to feel that 100 pounds down here, and over here, well, you'll be like, well, I don't really feel it, but I do feel it out. I still got to hang on because my feet are flying. You know what I mean? And then up here, well, you weigh more, so maybe you'd weigh less. Maybe it's easy to hang on to at the top. Because now you weigh less. You would have had to hold on with 100 pounds, but now you weigh quite a bit, so, yeah. Now I'm kind of confused, and I'll come back to because I'm just wasting your time. I don't think I can go from the horizontal one to the vertical. But anyway, go to this on YouTube to see if I even got the answer right, and I'll do that right now. I haven't even looked at this one. That's why we do these videos on the fly, to see if we can learn anything about anything, and it's learning the basics. It's setting up extremes to even figure out what the hell's going on, and it's amazing. Maybe this is just a made-up problem, but an airplane going 112 doing a loop, that sounds real slow, but I'm sure it can be done, and guess what? That's a video. Alright, we can't stop there, because you were just saying, hey, if a person is hanging on here, you know what I mean, isn't that going to be different than if they're hanging on, you know what I mean, here, on the outside of this plane? Well, sure, and that gets down to the whole F equals MA, because the universe the universe don't care, but if you can identify an acceleration, you got a force. You know what I mean? And if your detector is like, whoa, you know what I mean? Whoa, we got a force. Hey, guess what? You got some acceleration. Anyway, okay, so yeah, and what did we say? Well, do we have to do it again? So that acceleration, the component that was omega squared times the radius. The radius was 400 meters. That omega, that was real small. That was, no, for this problem it was 0.125 radians per second. So our acceleration is 400 times 0.125 squared. Our acceleration is 6.25 meters per second squared. F equals ma. And then we got 60 kilograms times 6.25. 60 times 6.25. Alright, so that's 375 newtons. We already said F equals ma if it's on Earth. That's going to be 60 kilograms times 9.8 meters per second squared. 60 times 9.8. And that's going to be 588, okay, newtons. So, you know what I mean, just the pilot on Earth is going to weigh 588 newtons. We're just going to stick in newtons. I think we get it. 375, that's like 100 pounds. You know, you got to hold on 95 pounds. Anyway, and this is 150 pounds. But anyway, so 588 newtons on Earth. But here, okay, and right here, what is it going to be? Well, it's going to be 588 newtons what you weigh, plus you're getting wung around in a circle. You know what I mean? It would be like, you know, the merry-go-round, you know, and all the kids are just like, whoa, just hanging on for, you know, gosh darn dear life. But then, and we know that this is horizontal, but then you take that merry-go-round and then flip it up vertical, and then you got, you know, kids hanging on. Well, right here, they're gonna, it's the force that they're hanging on with, that's extra. You know what I mean? They're hanging on with the 100-pound force before they fly off, and they weigh 100 pounds. Right here, they're gonna be, there's 200-pound force. You know, on the bottom, and then up here, if they're hanging on with a 100-pound force and they only weigh 100 pounds, well, they're just literally going to be a glob. They're going to be weightless. So see how on a merry-go-round, if you're hanging on with 100 pounds of force going this direction, but you only weigh 100 pounds, and then you flip that merry-go-round vertically, well, you're going to be 200 pounds here, and up here, well, your 100 pounds is going to subtract the 100 pounds that's trying to fling you off this thing, and you're going to weigh 0 pounds. So right here, you weigh less. So 588 minus 375. So you weigh half as much. You weigh definitely way more than half as much right there. You know what I mean? On a scale, you're like, whoa, I'm becoming weightless. But here, hell no. You're going to weigh almost twice as much. You're going to weigh 1.5 times your weight. Here, you're going to weigh, 0.5 times your weight. And here, it's normal. It's like your weight this direction, well, you're still hanging on with this 375 newtons because you're getting flung. So even on the merry-go-round, flip that merry-go-round up vertical, 100 pounds of force on you. Well, yeah, you weigh 100 pounds, but that's in the down direction, and you're still got to hold on with 100 pounds that way. So anyway, all right. So I think we get it, and but I definitely wanted to do that because now you can see at least those two, and yeah, and here. So you weigh more, you weigh the same. You know what I mean? Right here, you would weigh the same. And we already did that. This is literally this is the elevator with a certain velocity going up or down. And if you had a scale, you're going to weigh the same. But now over here on this part of the circle, well, you're going to weigh hella more. And then up here, you're going to weigh less. Alright, that didn't complete the whole picture, but that gets you a lot closer. And guess what? That's a video.